So far, everything has been translational motion. So everything we've talked about so far in this course is what we call translational motion. And what we mean by that is translational motion is where the center of mass of the object moves in space. So translational motion is motion of the center of mass. But we can also have an object that isn't moving its center of mass through space, but is simply rotating and around an axis through its center of mass. And in that case, then we would have rotational motion, and we have to now learn how to apply our ideas to that. So for rotational motion, we can imagine, say we have a disk that's rotating, and there'd be some center to it, and say that there's some point on this disk that we'll just put here. And as this disk spins, right, it's going to travel some arc length here. So this distance S is the distance that the point travels as the disk spins through an angle theta. So let's mark theta here. And as the disk spun through an angle theta, this point moved a distance S. So the distance that is traveled as this one point spins through some angle theta, where theta now, remember, is going to be in radians, then this distance S is actually going to be equal to R, which is the distance from the center to the point, times theta. So hopefully that's something that you've seen before. It's a refresher of the basic geometry of the circle. It makes sense, right, that if you go through 2 pi, then the circumference of that circle is 2 pi r. And so this then is just the small portion of that circumference, depending on what theta is, again in radians. Okay, so we can then talk about, this is the distance traveled, and so you can imagine that one point is basically undergoing translational motion. And so some things that we talk about make sense, but more commonly you want to come up with something that's true for every point on the disk and not just specific to that one, because one that's further out would have traveled a farther distance in that same amount of time. So now we can actually talk about what are going to be called your angular displacement, your angular speed. I'm going to write down all the terms and then I'll define them. So your angular displacement, your angular speed, and your angular acceleration. These are sometimes called rotational displacement, rotational speed, and rotational acceleration. Angular and rotational are sometimes used interchangeably. So angular displacement here would be how far it has gone in terms of its angle, right? So displacement before was delta x, now it's going to be delta theta. So the angular displacement is defined as some theta final minus some theta initial, and again this is used in radians. The angular speed is not, what's its distance traveled divided by the time, but instead it's going to be the rate change of the angular displacement, right? Before we had that translational velocity was delta x over time. So it makes sense that we would have angular speed would be then d theta dt, how quickly that angle is changing. And that's going to be defined as omega, so not a w, but that's a omega, and that's going to be in radians per second. And you can then have an average omega, an average angular speed, which would be equal to your angular displacement divided by time. And then lastly, the angular acceleration is going to be given by alpha, and that's going to be, as you might expect, d omega dt. So the rate change of the angular speed, or the angular velocity specifically. And the unit for this would then be radians per second squared, just like meters per second squared, but now we're talking about angular displacement. And the average angular acceleration would be equal to delta omega over delta t. Now, again, it's important to point out that these are going to be the same for all points on some rigid disk, right? So this is independent of where it is located. So these terminologies and these ways of describing this rotation of the disk apply to the entire disk. The disk has, some speed and acceleration and displacement in some given time. Now, on the other hand, when we start writing down the translational quantities for a specific point, we'll see that it will depend on this r value. All right, so you have all of these ideas for displacement, speed, and acceleration, and we had our kinematics equations for translational motion. So we want to recall that for a constant acceleration, we had the kinematics equations for now what we call translational motion. So we had, v final, for example, equals v initial plus the acceleration times time, etc. But it turns out that you make these same assumptions, and without going through the derivations of all, you can have your kinematics equations for rotational motion. So then you end up with rotational motion kinematics equations. And again, I won't list them all here, but you would imagine that v final, that would turn into your angular velocity. If time permits, we'll talk about the sign of the angular velocity, the direction associated with that. It involves something called the right-hand rule. But for now, you can say, well, you have your translational velocity. That would be your angular velocity, omega. So omega final equals omega initial plus, instead of your translational acceleration, your angular acceleration, and then times time, because time is just time regardless of what, whether you're talking about translational or rotational motion. So you have then this set of equations that you can then use for problem solving when appropriate.